Hello everyone, welcome to lecture 10 of the online course on modern display technologies, flat panel displays. Today's lecture will be on color gamut and light sources. So here is the lecture outline. We have been covering the fundamentals of colorimetry, and in this particular lecture we will just cover this particular topic called color gamut. We have covered about these things in the previous lectures. Then we will also look into the light sources, something like sunlight and black body radiators, light sources for transmissive, reflective and projection displays, color rendering index, and then we will look into production and reproduction of colors. So, what is color gamut? So, if you remember, this basically tells you about the range of colors that can be produced. So, when you see the CIE 1931 XYZ system, the boundary of this horseshoe shape of the chromaticity diagram basically is formed that connects the shortest and the longest wavelengths, right. So, we know that any spectrum can be divided into monochromatic components. So, it is very straightforward to understand that the color coordinate of a stimulus with a broader bandwidth lies away from the boundary of the chromaticity diagram, because along the chromaticity diagram's boundary you have the pure color where the bandwidth is the narrowest. So, as you keep on mixing the colors, you basically move towards the center of this horseshoe pattern. So, at the center of this 1931 XYZ chromaticity diagram, that means at this particular coordinate around 0.33, 0.33, this corresponds to white light with a wavelength independent light spectrum, and it also tells you that it is an indefinite number of different energy distributions can basically provide a mathematic color match for this particular color. So, that is what it tells you when you have wavelength independent energy spectrum. So, in this display or in any display for that matter, three primary colors RGB can be used to regenerate all the colors in an image based on the trichromatic color space theory. Now, by mixing the three primary colors, that is basically the colors mentioned within this triangle, as you can see here, these are basically color gamut which are the observable range in different standards. So, we will talk about two different standards here, one is NTSC and another one is BT 2020 standards. So, here they actually refer to two different triangles. So, you can see when the triangle is larger, okay, that basically corresponds to three primaries being very close to the monochromatic lights. Okay. So, in that case you basically have a larger color gamut because you can demonstrate more number of colors. Okay. So, such triangle is basically called the color gamut of the display. So, here NTSC basically stands for National Television System Committee standard, and also you have the other one which is BT 2020 standard. So, in this NTSC, the color coordinates for the red, the green, okay, this is this one, yeah. So, it is basically this one, yeah, NTSC the smaller one, and then you have this one as blue. So, what are the coordinates? This is basically 0.67 and 0.33, then you have this one which is 0.21, 0.271. So, these are basically the x and the y values, and the blue basically is coming from 0.14 and 0.08. So, these are the x y coordinate of the red, green and blue stimuli according to NTSC color standard. Now, if you look into the larger one, that is coming from the ITUR, that is the International Telecommunication Union, the radio communication sector, okay, they basically recommend this BT 2020 standard because it has got a larger triangle, that means larger color gamut. So, here the red, the green and the blue, they are more on the monochromaticity line. Okay. So, they are close to those. So, you can see the values for x, y, z in this particular case. So, here actually the three primaries are basically on the monochromaticity locus, okay, within this 630, then 532 and 467 nanometer respectively for red, green and blue. So, that tells us about the color gamut. So, larger is your color gamut. So, if you follow this standard PT 2020, you can basically display more ranges of colors. Now, we move on to color sources. So, what are the different color sources? So, the first one is the sunlight, and we will also talk about the black body radiators. That is important, okay, to understand how different color sources work. So, the importance of color sources is that the color sources are crucial for generating color stimuli, as the same object may look very different, okay, they may look of different colors under different ambient light. Just like when you go for evening walk, you will see that your skin may appear pale under the street lights, okay, at night. Now, the impact on reflective display is that light sources significantly affect reflective displays. They show different colors under different lighting conditions. So, what is the purpose of display? The display's job is to produce realistic color images, okay, as if they are illuminated by natural or artificial white light. So, any object that has been displayed in an electronic display should look realistic. A red apple should look as red in reality as well as on your screen. So, the first thing is the white standards in display. So, the displays basically include white standards to present the same image stimuli as the real object. So, for example, a display typically allows switching among different white standards based on the user's choice. Okay. So, the two very common white standards are basically these two, D65 and D93. They basically correspond to daylight with color temperature of 6500 Kelvin and 9300 Kelvin respectively. Okay. So, this is a figure that basically illustrates the color temperature of a black body, which is measured in Kelvin. So, you can see 1000, 2000, 3000 all the way up to 12,000 Kelvin is listed here. So, larger is the temperature, you basically move towards a bluish color. So, somewhere here you have the whitish pattern. So, the 6500 is somewhere here. So, this is basically the warm blue light daylight kind of thing, and 9300 is the cool blue light. So, you have this bluish effect, right. Now, the backlight modules in any non-emissive or transmissive displays, okay. So, you know that non-emissive display do not emit on their own, or any kind of transmissive display should have some backlighting module. So, there you basically require this light valves to first generate the light. Okay. So, one of the most important natural light that we deal with every day is the sunlight, right, and that is also a form of black body radiation, and you will see that the spectral power distribution depends on the temperature of the emitter alone. Now, understanding this will help you understand that what kind of spectrum you will get from your light valve. Now, when a black body is at uniform temperature, its emission has a characteristic frequency distribution that basically depends on the temperature, and this emission we call as black body radiation. So, the spectral density of the radiant power which you can measure in unit of watt per meter cube. For the black body, you can express it using this equation, which is very popular one. So, m lambda t will be equal to 2 pi h c square divided by lambda to the power 5 into 1 over e to the power h c divided by lambda k t minus 1. So, here m is basically the spectral radiant excitance, that means how much is the power per unit area per unit wavelength that is coming out of the radiator. Now, what are these other constants? H is the Planck's constant, that is 6.626 into 10 to the minus 34 joules second. C is the speed of light in vacuum, 3 into 10 to the 8 meter per second. Lambda is the wavelength in meters. K is basically the Boltzmann's constant, that is 1.38 into 10 to the minus 23 joule per Kelvin, and T here is basically the absolute temperature of the black body given in Kelvin. So, now let us look into the spectrum. So, with increasing temperature of the black body radiator, the radiant power increases. So, you can see here that the temperature is increasing. So, radiant power is increasing. Okay. So, this is the intensity graph, and what you see that the spectral peak is basically doing a blue shift. Okay. So, if you put this black body radiation pattern, or you can say black body locus, okay, on the CIE 1931 XYZ chromaticity diagram, this basically looks like this. So, you basically start with around 1500 Kelvin here from the red side, and slowly you move towards white and then towards blue. Okay. So, that is somewhere around 20,000 Kelvin. Okay. So, as I mentioned, the locus basically starts at deep red for low temperature, and then it passes through orange, yellow, white, and finally to the bluish white at very high temperature, something around 20,000 Kelvin. So, when the chromaticity coordinates of a stimulus basically lie on the black body locus, we can define the color temperature of the color stimulus, which is basically the temperature of the black body radiator at this chromaticity coordinates. So, there is a concept called correlated color temperature, or CCT. It is a metric that is used to describe the color appearance of light that is emitted by a light source. So, for light sources which are not perfect radiators, their proximity to this locus is used to determine their correlated color temperature, right. Now, a tungsten lamp is typically a black body radiator with the color temperature something around 2856 Kelvin. So, it is somewhere here, okay, 2856 Kelvin. So, from this color temperature scale, you can basically see that this is where this source is lying, and you can basically denote it as illuminant A by this CIE scale. Okay. Now, if you look into the CCT of sunlight at the surface of the earth, it basically ranges from 4000 to 25,000 Kelvin, depending on the observation time and the place, and due to also the absorption by the atmosphere. So, there an important concept comes into picture, which is basically air mass. Okay. So, air mass is basically defined as the ratio of the path length within the atmosphere for sunlight to reach the observation point to the thickness of the atmosphere. So, say this is the thickness of the atmosphere, okay, and this is the path length for the sun rays to travel through the atmosphere to reach this point here. So, this is P, and this is the direct, or you can say the thickness of the atmosphere. So, the ratio of this P and D is giving you the air mass. So, in this particular example, when the sunlight is basically observed from the equator with a solar elevation of 30 degrees, you see that this will be 30 degree, this is the solar elevation angle, So, this ratio will come out to be 2. Okay. So, you can relate it using the sin 30, okay, very simple. So, since this atmosphere basically absorbs light with short wavelengths more as compared to the long ones, the CCT is basically lower with the increasing air mass, right. So, this basically explains the observation that sunlight looks redder when it is towards sunrise or sunset, and it basically looks whitish in the noon when you are directly looking up. Okay. So, with that basic understanding of the natural light source, now let us go into the light sources for transmissive displays and use these concepts further. So, the important point is the backlight that is positioned behind the display. The purpose is to illuminate the screen. Now, what are the criteria for the backlights here? They should have sharp RGB peaks for primary colors, and they should be highly efficient so that you can reduce the power consumption, right. So, what are the backlighting technologies that are used? So, the previously dominant technology was cold cathode fluorescent lamps, that is CCFLs. So, they used to operate via glow discharge in mercury vapor and rare gas kept under low pressure. So, this produces cold light without any hot filament, and they used to offer efficiency greater than around 60 lumen per watt. But because mercury is carcinogenic and you are using it, okay, so there are environmental concerns due to the use of mercury and also the fragility of these tubes. Next comes LEDs, the light emitting diodes, which are now the primary backlighting technology which are used for LCD panels. Okay. These are more robust and environmentally friendly as compared to this CCFLs. Now, let us look into the reflective displays, where the light source is basically outside in the front of your panel. So, you can call it front light because these are positioned above the display to illuminate it in a dim ambient condition. So, what are the criteria of these front lights? So, they must be transparent and thin, and they minimizes the light emission towards the viewer side, so that you can get a optimum contrast ratio. So, what are the configuration of this front light panels? Okay. The emitter placement is important, like CCFLs or LEDs are positioned at the side of the display, and then light guide, okay, you should put transparent structure guides. Okay. So, you can use transparent structure that can guide light to the reflective displays, and the reflective display also modulates the light and reflects the image back to the viewer. So, there are basically 3 front light configuration. One is the emitter placement, okay, then that is important, then you have this light guiding, and then the modulation aspect. Next, we will look into the light sources for projection displays. So, what are the requirement in this case? You require high brightness and efficiency to project large and clear images. So, what are the different light source types used for projection display? The first one is gas discharge lamp. These are basically traditional choice for projectors. Then lasers are used. They have their advantages like narrow emission spectrum that significantly increase the color gamut because you get more pure colors to mix, okay, and then higher efficiency that reduces the power consumption. However, there are some challenges from this lasers, something called speckle effect, because this is caused by the interference from the laser's coherence light. So, that will basically reduce the image quality, but it can be mitigated by destroying the laser coherence. Okay. So, you can basically remove this effect to great extent. So, now let us look into another important topic, which is color rendering index. So, what is color rendering index? It is basically a quantitative measure of how accurately a light source reveals the true color of objects as compared to natural sunlight. So, you can understand the maximum score or maximum CRI value can be 100, right. So, when you have low CRI, it basically indicates color difference between the two light sources. So, what is the purpose of CRI? It basically evaluates the ability of a light source to render the colors of the reflective objects compared to a black body radiator. You can compare it to a sunlight also, and the reflective displays basically relies on external light sources. So, the color and the brightness depends on the light sources spectrum and intensity. So, having a good CRI is very important. So, how do you obtain the color difference? The difference of the colors can be calculated as absolute distance between the 2 points in the UCS coordinates, that is in the, like if you consider the 1976 L star, U star, V star color system, there you can take the difference as delta L star square. So, you are basically doing square root of delta L square plus delta U star square plus delta V star square. Okay. So, these are basically these delta terms are basically representing the coordinate differences between the two colors. Now, by choosing 8 different objects which appear slightly grayish red, okay, dark grayish yellow, strong yellowish green, moderate yellowish green, light bluish green, light blue, light violet and light reddish purple under daylight, okay, you can basically calculate the CRI for that source. So, CRI will be calculated as 100 minus summation of I for all these 8 cases. Okay. So, how these different colors will basically look into under that particular light source. Okay, and you calculate the color difference. So, delta EI star for all of these 8 cases you sum up and you subtract from 100. So, these are the standard colors R1 to R8 that are basically used in this particular color rendering index calculation. So, what do you understand? To achieve a high CRI, the spectrum of the color source must be broad enough to reflect the light from different wavelengths, right. So, the light source that has got a continuous spectrum such as an incandescent lamp, something like this, other than a fluorescent lamp where you have all the possible wavelengths present. Okay. So, they will definitely have high CRI value as compared to the fluorescent where only few particular wavelengths are only present. Okay. So, here you can see the fluorescent lamp has basically discrete emission wavelength. So, their CRI value is low, typically around 50. So, you can understand for a monochromatic light the CRI value can even go as a negative number. So, they are not good for production and reproduction of colors. So, with that we are starting this new concept here. So, what is the main purpose of your display? The displays are basically used to produce and reproduce color images. So, we all know that typically 3 primary colors red, green and blue are needed to generate all the colors due to the trichromatic color space generated by the human eye. So, in other words, you can say that these 3 primary colors were used to generate the same stimulation of the L, M and S cones as the real object. Okay. So, your eye should perceive those 2 colors as same. However, the spectra from the real object and the displayed object could be different. So, here is an example. So, figure A shows that the measured spectra, okay. So, this is the real object and this is the displayed object. So, they basically, so if you measure the spectra under sunlight, you will see it gives you a continuous curve, okay, for this region. Now, when you take a picture of the basketball and display it on a LCD monitor and then you measure the spectra again, you will see it basically looks like this, where it is not very continuous, you have some discrete spikes. So, in this case that you see in this particular figure B, the basketball color from the display basically consists of red, green and blue emissions, and this is very different from the real object how it looks like. However, the two colors from the real object and the display should appear the same. So, this is where the role of metamerism comes into picture. So, metamerism tells you that different spectral power distribution can still produce identical color perceptions. Okay. So, this basically allows or enables the displays to replicate the real world colors using RGB emissions, even though they have very much non-identical spectra. So, what is the key insight for color reproduction? So, color reproduction on displays basically relies on the concept or the principle of metamerism to ensure that the accurate visual basically matches to the real world object. So, the perception should remain same for the object, whether it is the display is giving the fill or it is seen under the real or the real object is seen. Okay. So, with that we conclude this lecture. If you have got any doubt regarding this lecture, you can drop an email to this email address mentioning the course name on the subject line. Thank you.